Hello friends, today we are going to study an experiment of type A step-down MOSFET chopper. Here, first we will understand what is a type A chopper. Type A chopper is basically if we draw a waveform of output voltage and output current, the waveform will lie in the first quadrant. As we can see in this, the average value of output voltage is also positive and the current average value is also positive. And if we go for type B, just for comparison, the waveform will lie in the second quadrant. The average value of the current will be in the opposite direction. The negative signs only indicate the direction. The current is actually not negative. Now, if we go for chopper circuit, this is our chopper circuit where we are providing AC mains through switch 3. Switch 3 is the control of the AC mains. Here is a fuse and here is a transformer. Then we are going for rectification of the AC into DC. Here are the rectifier diodes. Here is the filter capacitor, and this is the control PCB which we will study in some times. And here is the switch 2, so that we can adjust our load like resistive and inductive. If we close this switch, you can see the current will bypass and the load will be resistive. If we open the switch, the load will be inductive. Now we will go for the control PCB. A control PCB is a combination of many logic gates in which one Smith trigger and there are many comparators. A signal is given to Smith trigger, and these are the X7, X9 and X8 pin of the control which we have connected in the circuit. This is basically a power MOSFET. We don't need it much, so we will not go in detail about this circuit. Just we have to know that X7 and X9 is the connection of the power MOSFET. Now we will directly go towards the chassis of our circuit. So friends, this is our chassis. Basically, we are observing output voltage waveform and current voltage waveform. For observing the current voltage waveform, we have connected a current sensing resistor which is a value of 1 ohm. So we will calculate the waveform across that resistor and we will divide the value of resistor for that value of waveforms. So that will be the exact value of the current waveform because the value of resistor is 1 ohm. Now we will go for connections. We have to connect emitter. We have to connect voltmeter for observing the voltage. So for observing the voltage, we are connecting channel 1 of the CRO, and for observing the current, we are connecting channel 2 of the CRO. For emitter connections, we have to connect emitter positive and emitter negative with the load. So in this chassis, we have X14 and X15 pin to do the emitter connections, and we have X17 and X18 pin for the current sensing resistor, so that we can observe the voltage waveform across that resistor. So now we will go for the connections. We have connected X14 and X18 for voltage waveform, and we have connected S17 and X18 for current waveform. And for emitter connection, as we have to connect the negative of emitter towards the load, so we have connected X14 and X15 for the emitter connections. Now we will go for the circuit operation. So now we have to vary two control strategies. Here these are frequencies and duty cycle, and there are three switches to control this circuits. Switch 1 is to disconnect and connect the whole load circuit. That is, if I kept switch off, the load will be disconnected with the whole circuit. There is a main switch which is switch 3, and there is a load select switch which can by selecting that we can select inductive load or resistive load. So now we will turn on the chassis, we will switch on the mains, we will connect the load circuit by switching on the switch 1, and we will keep it in resistive mode. Now we have to vary frequency and duty cycle for our observations. Now we will go to the CRO. Okay, so here is the CRO. We have to first remove the ground lines for both the channels. Now we can see that the current and the voltage waveforms are similar. Now we will go for the calculations. This is for resistive load. We have to vary frequency and duty cycle. First I will keep a low frequency. This is low frequency, and duty cycle is also less than 50%. And first to avoid the confusion, I will remove one wave. This is voltage wave which is connected to channel 1. This is a V0. Now we have to calculate V0 value by calculating the divisions and the knob per division value. For current, we have to do the same. I will remove the voltage waveform. This is the current waveform. The readings will be the same. Now we will go for inductive load. For doing that, we have to make the load switch towards L. So it is now in inductive load. Now we will concentrate on the waveforms. As we can see, the current waveform and the voltage waveform is now not similar. Before there was a resistive load, so V is proportional to I, so the waveforms were similar. But now here is the inductive load, so the waveform will obviously be different. Now we can see that the current is going to a maximum value, then it is returning to a minimum value, then finally becoming 0. We have kept a frequency to a low value, duty cycle to a low value. This is the where the current is going to 0. This is called as discontinuous mode of inductive load. Now if we vary the frequency, we can observe that the waveform is changing and the current is shifting. I will hold this a little. Now we can observe that the current is not becoming 0. It is going maximum, it is going minimum, and then it is going maximum. This is continuous mode of chopper circuit. This happens only in inductive load. It doesn't happen in resistive load. So this is the discontinuous mode, and the readings will be the same. This will be the I0 and this will be the V0. Here we can observe that the freewheeling diode time is almost equals to T off. For observing the freewheeling diode time, we have to decrease the frequency so that the freewheeling off time is less than or T off time. Now when we decrease the frequency, I will maximize the voltage waveform so that we can observe the freewheeling time. Now we can see a curve wave. This curve wave is the time period of the freewheeling diode. If I increase the frequency, this curve is disappearing and it finally disappears. That means the freewheeling time is now equals to or T off time. So we can calculate the freewheeling time period by calculating the divisions of the CRO. Now we will go for a DC voltage calculations. Now we will calculate a VDC, which we have stepped down from the 230 mains voltage. VDC we will calculate after the rectifying of the diodes. So the voltage across the capacitor will be of VDC. Now we will calculate VDC in a DMM. VDC for VDC, we have pin X12 and X13. Now we will keep a pins, and yes, we have stepped down to 34. From 230 AC mains, we have stepped down to our DC voltage to 34 volts. Now for calculating the load resistance, we have to remove the emitter which we have connected in X14, and we have to calculate the load resistance from the negative of the emitter to the negative of the voltage. So this is X15 pin and X18 pin. For doing this, first we have to switch off the mains and then we have to select for resistive and inductive. First I am doing for resistive load. For resistive load I am calculating the load resistance, which is 26.7 ohms, and I am changing the switch to inductive load, and for this the load resistance is 26.9 ohms. So this was the experiment of type A step down MOSFET chopper. Thank you guys.